questions. We're at the start of week 3 for Chem 124. We have questions about the homework and the emissions lab. So, which one do we want to start with? Homework questions or lab questions? Homework. Okay, so let's go ahead and do some homework questions. What questions do we want to address?
16, I think, was a popular one.
16 is a popular one. Any others we should look at? We'll just start a whole list and then we'll look at that list together.
22 and 23.
Okay, we can look at 22 and 23. The quiz is only up to problem 18 because we haven't covered that material in class yet. I'm okay getting ahead. I'm okay getting ahead, but if you looked at the on the board at the end of the day, I put homework quiz 2, and then underneath it was 1 to 18.
Okay.
So we haven't gotten to that stuff yet, but I'm always down to get ahead if you want to get ahead. It's always a good idea. So 16.
Yeah.
Any others?
17 and 18.
17, 18.
12.
12.
Oh, I see 11.
11. 11's a good one. Any others?
14.
14. That seems like a good start. That should take up a good portion of time. Let's go ahead. Let's start with, we'll just go in numerical order. So we'll start with number 11. Someone do me a favor, read out what's number 11. I think that's the heat lamp one?
Yeah.
So we want to practice a couple things as we read through this, right? We want to be doing our question analysis as we read the question. So let's go ahead and read the question. I'll write down the things that I think are important as we read.
A heat lamp produces 32.8 watts of power at wavelength 6.5 micrometers, 6.51 micrometers. How many photons are emitted per a second?
So notice, the first thing I did is, as you were reading, I was already kind of doing some analysis. I wrote down the 32.8 watts. I wrote down the numbers, and I wrote down what the question actually was. There's another piece of information that's important on that that's after the question.
1 watt is equal to 1 joule per second.
Whoops, that's not what I meant to write. 1 joule per 1 second, right? So we can look at this and we can say, okay, we can do some problem analysis. We can kind of do some conceptual thinking behind the problem. We want to get to photons per second. We've got information of watts. That's going to give us information in joules per second. I've got to get something. If I want to get to photons per second, I'm going to need something that gives me information about the energy of a photon. So I can think about this, and I can say what equation is going to give me information about energy of a photon.
E equals hc over
Lambda, wavelength, right? And so we can call this E sub p. This is the energy of the photon equation. This is a combination of two things. This is E equals h nu and nu equals c over lambda. I plug c over lambda in there. I get equals hc over lambda. This is the equation we're most likely to use in this class, because most of the problems we're going to be dealing with is going to be about the energy of the photon related to wavelength, not related to frequency. So this is the equation that we're going to use. This will give me something in terms of joules per photon. I've got something else that's going to be, let me see, I want to write this in a little bit of a different order just because I know how it's going to work out. So I've got something, the first piece of information I have is something that's in joules per second. Then I've got something that's in joules per a photon. And I want an answer that's in photons per second. So from this, you can pretty clearly, we can think about what mathematical operation is going to get us. We can think multiply, divide, add, subtract. Addition and subtraction isn't going to make sense. That only works when the units are the same. These are not the same units. So those are bad choices. And then if we multiplied, we would end up with joules squared per second photon. I don't know what that would mean. So that's a bad choice as well. So we're going to divide, or we can think about it in terms of multiplying by the reciprocal. We can have joules per second times photons per joule. That's going to give us photons per second. So, the joules per second, this information is given. And then we can also calculate this one. Right? So that gives us our two pieces of information. The other way, so this is kind of looking at it in a couple different pieces, right? We're looking at it in terms of the information that's given, the equation that the problem suggests just from the vocabulary used in the problem, and then we did unit analysis to kind of get through all of this. We can also begin our thought process and say, how many photons do we expect? Just off the top of our heads, if we're going to have 32 watts worth of photons, does each photon have a lot of energy or a little energy? Little energy. How little of a little energy? Do you remember the order of magnitude for the energy of a photon? Just from doing other calculations, kind of just seeing it over and over again.
Is it about 10 to the minus 19?
Yeah, it's on the order of 10 to the minus 19. So when we say a little energy, we're talking like a little energy, right? 10 to the minus 19 joules per photon. So if we wanted to get to 32 watts, we'd expect the reciprocal of that number. We'd expect something on the order of 10 to the 19, positive 19 photons in order to get to this energy. To get it specifically, we actually do the calculation. At this point, you all could probably do the calculation, right?
How would you set up the calculation?
Let's still do it together just to make sure we are correct about that. So, we know that this is going to be 32.8 joules per second. We know that this is going to be, I'm going to write it in a little bit of a weird way, 1 divided by 6.626 times 10 to the minus, actually I don't like writing it that way. Let's just calculate the energy of the photon separately. Let's calculate this. So we're going to have the energy of the photon is equal to 6.626 times 10 to the minus 34 times 2.99 times 10 to the 8. That's going to be divided by 6.51 times 10 to the minus 6. I've gotten a little sloppy with my units. This is units of meters. This is meters per second. This is Planck's constant is joules seconds. If we also look at the units of joules, which is kilograms meters per second, meters squared per second squared, this units will work out to where we just get joules. The seconds will actually, you don't even need to look at that. The seconds cancels out, the meters cancels out. We're just going to get joules. Someone help me out, plug that into a calculator real quick.
Where did you get the 2.99 times 10 to the 8?
Speed of light,
Speed of light, okay.
right?
That's
So
the,
constant, that's the lowercase c.
yeah, so the H and the C are both constants?
Both constants.
Gotcha.
H is Planck's constant, c is speed of light.
3.277 times 10 to the 19.
Positive or negative?
Positive.
That doesn't sound right.
Oh, I have the reciprocal, my bad.
Oh, you did the reciprocal already?
Yeah.
Okay. So, what's the, we can put that in here. Give me the actual value, but I'm going to write that down now. 3.27 times 10 to the minus 9. What's the before reciprocal value?
Yeah, 3.05 times 10 to the negative 20.
Yeah, about that too.
Okay. Now, this is still in the order of 10 to the minus 19, right? You notice this is a longer wavelength than most of our light and other things. So this longer wavelength should have a lower energy because of that inverse relationship between wavelength and energy. If we take the reciprocal of this, this is going to be 1 divided by the energy of the photon, 3.05 times 10 to the minus 20. We get this number, that's 3.27 times 10 to the 19. You'll notice, even though it's not necessary, I will often explicitly put a positive for my exponents, because in chemistry, so many of our exponents are negative. If I don't see a minus sign, I am instantly like, oh, I forgot a minus sign. If I explicitly put a positive, I'm like, no, I must have meant to do that.
So did we solve for the the joules per photon? So like we had to like switch it up, or
Yeah.
we
So
understood
this
what that was?
this ends up being joules per photon. And then if we looked at this, we're going to divide by that number or multiply by the reciprocal.
That
So
makes sense.
we're multiplying by the reciprocal. This is going to be 1 photon is this many joules. And then, of course, we're going to get a huge number because we need a lot of photons to get to this level of energy. So if we do 32.8 divided by 3.05 times 10 to the minus 20, or 32.8 times the reciprocal, we get something along the lines of, what's that? Big number.
1.075 times 10 to the 20. So the 20.
10 to the 21.
21. Okay. Because we got 10 to the 19, we got 3 times 3, that's going to be like 9, but you've got some extra points left over, so it probably hits 10. And then you got 10 to the 19 times something that's like in the order of 10, so 10 to the 21. Yep, looks great. So this gives us an answer. Come on, and you can put your backpacks underneath things. So that's number 11. We should get something that's like 1.075 times 10 to the minus 21. Notice though that there's a couple different approaches we could take. We've got the logistical kind of just what do we expect from our previous experiences. We've got the unit analysis type way of going about it. And then we've just got the what numbers does the problem give us to work with. And the reason I'm going over all of that rather than the chemical principles or the physical principles here is because, again, I really see general chemistry as a problem-solving class. Like, how did we solve this problem? What information did we have? What context was it in? How do we use that to get to what we're trying to solve for?
That's a good question, just like general. In terms of quizzes, like, should we ever expect like a past homework question to pop up? Like,
So,
like
yes-ish. So, for example, on our next quiz, 19 to 24, whatever it is, the end of homework 2 will be on the next quiz.
okay.
I'm tempted to say the end of homework 1 could be on this quiz, but I didn't say that in class. And I don't like surprises on quizzes. And it was only one question. So this homework will only be homework 2, 1 through 18. In the future, I'll be explicit about when that's possible.
Okay, I just want to verify.
Yeah.
Okay, great. Thank you.
You bet. Any other questions about number 11? Pretty straightforward once we see it, right? I mean, literally, all you needed to do to show your work was this, right? All of this was our thought process to get to this, but it's one line of math. Like, mathematically, what we're doing is not that challenging, but there's a lot of concepts that go into that. I'm going to erase this and we can move on to number 12. What is number 12?
Says label each transition as corresponding to emission and which corresponds to absorption. Put the list in approximate, no calculation order of increasing energy transitions, so like smallest to largest.
Mm-hmm.
And then it's got an A, B, and C. So your A is going to be n equals 3 to n equals 1. Your B is going to be n equals 2 to n equals 4. And then your C is going to be n equals 4 to n equals 3.
So this is a little bit of a reading question. I'm assuming you're reading the textbook. This is also a little bit of a can you put it together question. We had 2 parts of information. We had we had En for hydrogen. This is particular to hydrogen at this point. Equals negative Rydberg constant times 1 over n squared. Right? So we can use this and we can say, we could calculate all 6 of these values, right? We can plug in n into each of these, we can calculate this, we can do it explicitly. But this is asking us to do it again in a more conceptual way. So the part that's reading is the definition of we talked about this in class as well, with the definitional difference between absorption and emission. Absorption was the atom gains energy. N value increases. Forgot how to spell increases for a moment. Emission is the atom loses energy. 2 O's or 2 S's?
I think
Just one of each.
one of each, yeah.
So the E sub n,
Mm-hmm.
what is that of? Because I understand for like the other ones, they change like delta E. And when you
So
have
this
two
is
different ends, it depends on which sort of orbital you're transitioning from. But if there's only one n in that equation, then there's
So,
two ends above.
right. So this is the energy of each level,
Okay. I see.
right? So the Rydberg equation is actually a relatively simple put together of two equations that we looked at in class on Thursday, which is we looked at the equation, the energy equation for an individual level, so we can look at the energy for each single n value.
Okay.
And we said the change in energy is going to be equal to E2, or let's call it E final minus E initial, right? Change in energy. So now if you just plug those things in, separate out the Rydberg constant, you get the Rydberg equation.
I
So the Rydberg equation puts these two equations together, but notice we don't actually need the Rydberg equation to think about this problem.
Right.
We need the definition of what absorption and emission is, and then we just need the fact that it's going to be an inversed value. Right? So we can draw essentially from this inverse value, we can draw the same kind of energy level diagram that I was drawing in class, where we have our E1, we have our E2, we have our E3, and we have our E4. And I drew it this way in class, and I'll draw it this way again in class today, where the levels get closer and closer together. And only one student came up to me after class and was like, was that intentional? I said, yes, very much so. And it's because it's an inverse n squared, right? So this would be like Rydberg constant divided by 1, Rydberg constant divided by 4, Rydberg constant divided by 9, Rydberg constant divided by 16, right? Each step, the difference between 1 and a quarter is 0.75. The difference between a quarter and a ninth is going to be much smaller than that. The difference between a ninth and a 16th, even smaller than that. So these energy levels actually, and we could keep going up to 5, 6, 7, 8, 9, 10, 11, 12, 13, right? This goes to n equals infinity. I just get tired of drawing the lines. And it also gets really difficult to draw the lines with like distinguishable distances between them once you get above like E7, right? Once you get above n equals 7, the lines are almost stacked on top of each other. That's going to lead to band gap theory next class, like on Thursday. But the lines get closer and closer together. So we can look at this and say, okay, so if I'm just looking at C, that's 4 to 3. That's the difference there. It's going to be pretty small. If I'm looking at 2 to 4, it's there. If I'm looking at 3 to 1, it's there. And just this visual piece, without doing, we could, with just that first equation, calculate the n values of all of these and then calculate the differences between all of them, which is actually doing the Rydberg equation in 2 steps, right? Rather than combining those two things together. We can also just do this visual representation and say anything that ends with E1 or involves E1 is going to be a pretty big change. Anything that involves E2 is going to be somewhat significant. Anything with E3 or less is going to be really small. Notice with these blue lines, I haven't said which are absorption or which are emission yet. We can actually answer the order problem of magnitude before we answer which are absorption and emission. To answer absorption or emission, we look at the definition. We say, if the n value is increasing, that's absorption. So 3 to 1 is a decrease I represent that by drawing the arrow as if it's going down, and that would be an emission. 2 to 4 is an increase, draw it as an arrow going up, that's an absorption. 4 to 3 is a decrease, that would be an emission. And notice, this is the thing that's important to me. The Rydberg equation by itself kind of neglects whether you're talking about absorption or emission. And also notice it depends on which version of the Rydberg equation we're using. There's 2 different versions with 2 different Rydberg constants.
Energy 1 versus the 1 over wavelength?
Yes.
Okay.
The 1 over wavelength equation, which I don't like to use, only works for emission. Right? That is the original equation that Rydberg wrote down based on the empirical observations he made. He saw the lines, he was like, hey, if I make it count like 1 over n squared, I get an equation that gives me the wavelengths. Didn't understand why it happened at all. We're approaching this from the opposite side, right? We said, look, Maxwell-Planck came along, said quantum mechanics is a thing. Schrodinger jumped on board, wrote this equation to take care of the energies. And if we fold through the entire quantum mechanical calculation, we get this equation, which explains why it's 1 over n squared. Right? This came out of solving the big, long, scary equation I showed you all. Like this 1 over n squared comes out of it naturally and confirms the Rydberg equation. The difference is this is the energy of the atom, not the energy of the photon. And we're going to talk about that difference in that detail in class today.
Energy of the atom or the energy of that level? It seems
So,
like there's multiple n levels.
right, so
electrons.
it's the energy of the, let's be real, so there's a lot of careful language we have to use around this, right? Because when we're just looking at the n values, we're just looking at the energy of the levels. But when we're talking about a physical process, we're talking about the energy of the photon exciting an electron to that level. Or an emission would be that electron relaxing and releasing a photon, right? So it's actually a dynamic process we're trying to describe. This would be energy of the level in a hydrogen atom. This would be the difference between 2 energy levels.
And so is it the case that the Rydberg equation only works for hydrogen-like atoms? And as soon as you start having other electrons, it doesn't work because you're shielded?
Yes. So there are some fixes. So the Rydberg equation works particularly for nucleus with 1 electron. So there are things that we can approximate, and there are corrections we can make that still is kind of like that, right? That's where you can get into effective nuclear charge, shielding, all of these different things. There are fixes to it to try and make it work better. You can all scoot in a little bit more, if you don't mind sitting on the floor here. You can pull in more chairs from the hallway if you want, but let's keep our backpacks like underneath chairs and stuff like that. So there's fixes we can do that allow us to approximately use the Rydberg equation for other atoms, but it's all approximate. And it's like good enough without going into like a full-blown quantum mechanical calculation, which is actually going to have its own approximations anyway. Question here and then there.
I just have a quick question. So like the energy levels are getting like close, like delta
Yeah.
G is decreasing. Is that what we see on the spectrum too? Is that why the lines are like get close to the distance between them? Or is that just a coincidence?
I'm gonna have to think about that one. I think the answer is yes. But let me think about that for a minute.
Okay.
Because the biggest energy transition is going to be, well, it's like smallest energy transition. No, there's some weird inverse relationship happening there. But I ultimately, yes. The problem is the lines are differences, not levels.
Okay.
Right? So when you go from this one to this one, as you get larger, like each successive like difference is going to be a smaller and smaller difference.
Okay.
But that's why I was inversed in my brain and I was like, why isn't this working? It's because you're not looking at the levels, you're looking at differences between the levels.
Okay, cool.
But yeah, actually, yes. Question.
If we got a question like this on the quiz, how much work would we need to show? Or
So
would it just be
notice
like,
this question did not require much work. Actually, we've talked a lot about the concepts, the definitions. I expect you to get these from reading the textbook and the definitions. At least read the definitions at the back of the chapter. But all you'd have to do is say, label this as emission, absorption, emission, biggest energy, smallest energy, middle energy. That's all you actually have to do, right? All it says is label these things. The catch is, if you get it wrong and you show no work, I can't give you partial credit. If you draw this diagram and you do something silly where you inverse your numbers and you're like, this is E1 and you count the wrong direction, you can be like, oh, you just made one mistake. I'll probably still give you a significant amount of partial credit because your mistake is just a labeling convention, not a mistake in the concepts. So you don't actually have to show much, but the more you show, the more likely I am to be able to give you partial credit.
So when you talk about a transition in energy, it seems like you're just talking about the magnitude, not the direction so much.
So there are two ways to think about it, right? Yeah. So when we talk about transitions, when we talk about the wavelength of the photon, it is magnitude. When we talk about the energy of the atom, it's absorption or emission. And also, conceptually, we've also seen how different absorption is from emission. Right? Absorption phenomena was the spectrometer with the food dyes. Emission phenomena was electricity and fire to excite and then see what's happening. Absorption happened when everything was kind of starting at a lower energy state and we were pumping it up by shining light on it. Emission was we're pumping energy into it to get everything excited, and then we're seeing what happens as it relaxes. But in terms of the magnitudes of the energies, these two things are actually the same. It's just the directionality and the initial state that gives rise to the difference between the two. Man, such good questions. You guys all have to ask these questions during class. Or everyone has to watch the video. Sorry, yeah, other questions.
So the Reinberg equation gives that thing, and you can calculate the wavelength of your photon based on the level. Does that mean that like the wavelengths are also somewhat quantized? If you just calculate the wavelength from n, which is quantized, and it's just an equation, or
so not exactly.
Okay.
Right. So if you're talking about the wavelengths of light produced from an atom, yes.
Okay.
Right, because you can only have particular wavelengths of light produced from an atom. But from a simple hydrogen atom transition, that is not the only way we produce light.
I see.
Right? So if our only source of light was ground state hydrogen, not ground state, but hydrogen emission at a particular energy level, like at a particular energy input, the world would look really weird because we'd only have 3 wavelengths of light that would exist. But because there's a lot of other things, like these lamps use mercury, the sun is burning like pretty much dozens of different elements and creating plasmas and going through like black body radiation, which we're going to talk about briefly today. There's all these other ways that we end up producing light. So light, as far as I know, can have any frequency associated with it, which means it can have any energy associated with it. The catch you get to is until you get down to the individual photon scale. There's a limit to the fineness of the scale, right? And that's what Planck's constant, I don't have Planck's constant written up here, but that's what Planck's constant actually represents. It's like, it starts to represent what's the energy of an individual photon.
Okay.
So there's a limit to how, so technically, it is quantized, right? That's the whole idea it comes from. But the atom is a much broader scale than light is quantized to, right? You have to get down to individual photon energy and minimum photon energy, which we're not going to do in that class. That's like a modern physics question. Like we're kind of off chemistry a little bit now, but it's really interesting. Any other questions? Should we see what number 14 looks like? Okay. Yeah, energy quantization. It's really neat, but you start to bump into philosophy pretty quick. It's like, what does it mean to be quantized? How detailed do you have to be to say, it's like It's like how many people are in the state versus how many people live in your house. You know, people are quantized. There's individuals, but there's several million live in California and like only a few in your house. So like, at what point does like the individual matter versus the collective? Like, right? So depending on how detailed you want to look, it's like, of course, individual
Why is this
matters.
stuff so small?
Yeah. So the problem with photons is the step is so small that we don't really, at least as chemists, we don't run into that as like a limiting factor very often. Let's see, we did 11, 12. What's problem 14 got going on? And then I want to do, and then 16 is next, so we're good.
It's kind of similar to like the last one, but we're actually calculating. So it says, use the Rydberg equation to calculate the energy in joules and the wavelength in nanometers of the photon absorption associated with a hydrogen atom undergoing the transition from n equals 1 to n equals 3. And then it says what part of the electromagnetic spectrum is the absorbed photon in.
So notice the problem already gave us a bit of information that we could have gotten from problem 12. It's 1 to 3, so it's absorption, where the atom is going to increase in energy, but the photon is going to be positive energy. The photon is always positive energy. So we can do this just using the equation that we learned in class last time, where we've got En equals negative Rydberg constant times 1 over n squared. And we can say E1 is equal to negative Rydberg constant times 1 over 1. And E3 is equal to negative Rydberg constant times 1/9. Take the difference between the two, and that's going to give us the magnitude, which is going to give us the energy of the photon. Because for the photon, it's just magnitude. For the atom, it's direction.
So it's final minus initial. Would it be E3 minus E1?
Yeah.
Okay.
Let's see. Yep. Final minus initial.
And then Rydberg constants, is it 1.097 times 10 to the 7?
What's the units on that? So that's where we have to be careful, because there are two different versions of the Rydberg equation. So if we put this together, we could get delta E, and I'm going to specifically say delta E of atom on here is equal to the negative Rydberg constant times 1 over n final squared minus 1 over n initial squared. I've just put those two equations together. This Rydberg constant needs to be in terms of energy. If I remember correctly, it's 2.18 times 10 to the minus 18 joules.
Yeah.
Cool. 2.18 times 10 to the minus 18 joules. The other version of the Rydberg equation is 1 over lambda equals negative r times 1 over n2 squared minus 1 over n1 squared.
Why is it 1 and 2?
I try to make it explicitly different, right? Final initial doesn't really matter. I mean, it's still final initial. This would be your second n, this would be your first n. Here's the catch, though. Oh, and no negative sign, actually. Does someone have the equation sheet?
Yeah.
Yeah. So, however, let's see if I can get this right. And 2 must be less than n. No, n1. Let's see, n2. No, n2 has to be less than n1. Sorry, inverses always mess me up. So
on the equation sheet it says it's 1 over n1 squared minus 1 over n2 squared.
okay, we can do that. And then I've just got to change my however. Because essentially, in order for this equation to work, it only works for emission. This side of the equation has to be a positive value. So this works because this is taking into account essentially just emission. So we're only taking into account one of our two possibilities between absorption and
Can we
emission.
make this equation work for absorption by like adding an absolute value sign?
Yeah, I mean, that's essentially what we're going to be doing with this one,
Okay.
right? So in this case, I need this number to be bigger, so I need n1 to be less than n2, right? So if this was 1, this could be 2, 3, 4, and this thing would be positive. If this was 2, this could be 3, 4, 5, and this thing would be positive. So there's that however that gets tossed in there, which isn't on the equation sheet. This is just knowledge, but I don't like this one as much. I feel like this one is much more flexible.
So can you just go over like quick spark notes of when you should use
each equation and
So essentially, these two equations can be used pretty almost interchangeably for emission, right? As long as we're doing emission, we could use either one. They're both going to give us the energy. This one's just going to jump to giving us the wavelength. You're going to have a different Rydberg constant that's going to be in terms of inverse meters, inverse wavelength. This one, you're going to have the same thing, except for you're going to get the energy of the atom, and then you're going to say the change in the energy of the atom is equal to the, there's going to be a second step, essentially, which is going to be the change in energy of the atom, absolute value, is equal to the energy of the photon.
okay. Gotcha.
So,
Or I guess
no, because the energy of the photon's always positive, so the atom could be positive or negative, but we always want the positive version of it. So, regardless, so whether the atom is gaining energy or losing energy, like if you're looking at a 1 to 3 transition or a 3 to 1 transition, the photon's going to be the same wavelength, same energy. But the atom is going to be either gaining energy or losing energy. This equation in black only works for the emission case because it jumps to the wavelength that skips this step. So to skip this step, you have to have this kind of absolute value that we mentioned earlier. Yeah.
Just quickly, what's the correlation between photon energy and wavelength?
So that is, oh, what is it?
That's what I'm totally blanking right now.
Anyone else?
CH or something.
HC over lambda, that
Okay,
one.
thank you.
Yeah, so that's the energy of the photon, HC over lambda.
The Rydberg constant is different.
Yeah, so this Rydberg constant is the 1.07.
Okay.
This one is 1.07 times, is it 1.07? 1.09 times 10 to the positive 7 inverse meters.
And that's found by dividing the original Rydberg constant by speed of light and
Oh, yes. However, what's the original Rydberg constant? So, when Rydberg originally did his work, this is what he wrote down.
okay.
He wrote it down just in terms, he did it only for emission. So, you know, those hydrogen lamps we were looking at, you're only looking at emission. You can look at just this equation because you're just looking at emission. And he was like, look, I noticed the lines for a lot of these atoms follow this 1 over n squared pattern. I don't know why it does that, but I notice it. And from noticing that was like, I can write this equation that tells me the wavelength related to this 1 over n squared pattern.
Okay, so in fact that's the original.
So this is technically the original. This is the one that comes out after we understand quantum mechanics and the photon energy.
Okay.
Rydberg actually did his work before photon energy and quantum mechanics were understood.
Okay. Makes sense.
And that was like one of the great successes of quantum mechanics was like, hey, we explained a phenomena that somebody already described but didn't explain. We got the same description, but now we also have an explanation to go with that description. So that was like considered like explaining like this, the explanation quantum mechanics offered to this equation was considered one of the great successes where people were like, whoa, maybe this thing is real. Quantized energy, who knew? But yeah, at that point, we can plug this in and we can continue solving. But I think, again, after we do the conceptual work, the mathematical work's not so bad.
What did other people get?
Yeah, what numerical value did a couple of people get for their final answer?
1.94 times 10 to the minus 18 joules for the energy of the photon.
I got that.
1.9.
It also has us calculate the wavelength. So do you use the 1 over wavelength?
I would just use this
Oh, you
one,
would just
right?
use
If
that
you've
one.
already got the energy of the photon, you can just jump to this.
And will we be given scale? Is that on the equation sheet? Of, like what? Because I believe the question asks, this is 14. Says what part of the electromagnetic spectrum is the absorbed photon?
So I expect you to learn 3 parts of the electromagnetic spectrum. Visible,
Sure.
ultraviolet is, you know, smaller wavelength, and infrared is larger wavelength. As long as you can get those parts, I'm happy. All
Do you
the
have
other
to know
details.
the numbers?
So yeah, so as long as you know visible, then you're good, right? Visible is 400 to 700.
Anything more or less?
Anything less than 400 is ultraviolet. Anything more than 700 is infrared. good enough for me. Now, of course, there's more gradations up there. You get into radio waves, you get into gamma rays, you get into all kinds of other things. X-rays, gamma rays, infrared, radio waves, microwaves, like all of that's there. But if we can just get those three, which really means just remembering visibles 400 to 700, I'm happy.
Nanometers, right?
Nanometers, yeah.
1.94 times 10 to the negative 18. Yeah.
And what'd you guys get for wavelength?
So 10 to the minus 18, that's pretty big energy. I'm guessing it's someplace in the ultraviolet, someplace less than 400.
I got 103.
Nanometers? Yeah, I
Yeah.
got that.
Which I think is still in ultraviolet. I don't think that's pressing into X-rays yet. So if you said ultraviolet, I'd be like, good enough. Should we take a look at number 16? That was the question that most people wanted to see.
Or the homework was just like 1 through
18.
Okay.
Yes.
Sub 22 and 23. Are we gonna
Correct.
get to that?
We're going to get to that.
Yay.
We will get to that.
Yeah,
This is the one.
Okay, so that was 14. What was problem 16?
I had a chart and some for unknowns.
No. That you're talking about
Dang it.
17.
That was 17.
16 is 5 lines in the hydrogen atom spectrum have the following wavelengths in nanometers.
Wait, let me switch colors real quick. So it looks like a different problem. Okay, we've got 5 lines.
The first wavelength in nanometers is 121.56. The second is 434.05. The third is 486.13. Then 656.28. And last 1093.8.
Hey, Dr. Ecker, do the live streams get saved?
Yeah, and
Okay,
posted to
cool. So
my
we just watch it.
YouTube. Yeah.
Alright, awesome. Cool. Thanks so much.
No, I see it.
Yeah.
So we've got these different lines. What the heck are we supposed to do with these?
Identify which transitions are visible in the series n sub f equals 2, the infrared series, n sub f equals 3, and the ultraviolet series n sub f equals 1. And then calculate n initial for each emission line.
This problem is actually giving us a lot of important information that you could get out of the textbook. It's telling you about the Paschen series, the Balmer series, and the Lyman series, named after the different scientists that originally observed the visible spectrum of hydrogen, the infrared spectrum of hydrogen, and the ultraviolet spectrum of hydrogen. That's important information. You get it in the textbook. You also get this visible information from the background of the lab. So there's 2 places you should have seen it. Third place you see it, this problem. We're also going to talk about it some in class today. So there's, like, again, repetitions, right? Ultimately, we could go back to the equation for an energy level in a hydrogen atom and just calculate all of the possibilities. Right? Calculate all the possible energies for n equals 1 all the way up to n equals 6 trillion. It might take us a bit. And then calculate all of the differences and say, hey, which ones correspond to visible, which ones correspond to infrared, which ones correspond to ultraviolet. And it turns out, after you get out of infrared, anything above 3, you just go further and further into the longer wavelengths. You go into the more infrared, a lot more infrareds. I don't think you might hit some microwaves, but I don't think you're going to hit radio waves just because you hit the limit of hydrogen's. This way the energy levels get closer and closer together, your deviations just get smaller and smaller. But we can go ahead and look at this, and we can pretty easily split this up, especially with the information we just talked about. A, B, C, D, E. Which one's infrared?
A.
Oh, infrared.
E.
E. I did it backwards just to trick y'all. Which one's ultraviolet? What are the rest?
Visible.
So that means we just solved for n final through our knowledge of the electromagnetic spectrum. We now know the n final value for all of these transitions that are observed. So this is going to be, let's write that properly. This is going to be n final equals 3. This is going to be n final equals 2, n final equals 1. Now, if n final equals 1, what could n initial be?
2.
Or,
3.
or,
Infinity.
or, yeah. Just keeps going, right? If n final equals 2, n initial could be equal to, and the reason we're just counting up is because this is specifically for emission, right? So n initial must be bigger than n final. So n initial can be 3, 4, 5, 6, all the way up. This one, n initial could be 4, 5, 6, 7, all the way up. Now the question becomes, how do we know which one it is? This is our could be's. Right? But we don't just want to could be, we want to know what it actually is. This problem, even though I just told you I don't like this equation, this problem is particularly well suited to the 1 over lambda situation. Equals special Rydberg constant, or original Rydberg constant, whichever way you want to think about it, 1 over n1 squared minus 1 over n2 squared. The reason it's particularly well suited to this equation, even though I don't like it as much, is specifically an emission problem. And it explicitly gives us wavelengths. So using this equation is essentially going to skip a couple steps for us. We could also use the fact, we could also use the HC over lambda equals absolute value of negative Rydberg constant times 1 over n final squared minus 1 over n initial squared. Where now we have to be careful about making sure that we're doing everything correctly. We know that the n final minus n initial is going to be, because it's emission, n final is always a bigger number, so we know that this is always going to be positive. This whole thing is always going to be negative because emission is the atom losing energy. The absolute value says the photon's going to be positive energy. So we could use either one. And as I think somebody pointed out before, the difference between the original Rydberg constant and the Rydberg constant we like is just this factor of hc. If you take ry, divide by hc, you get r. So you could actually use either equation. And you'll notice I skipped a couple steps here. I recognized already energy of photon equals hc over lambda, and I recognized that the change in energy of the atom is equal to the energy of the photon. So I put all of that together. See it? So I put that all together. The reason that the equation in black is a little bit easier to use is because it already takes into account the HC. It's just going to save us a couple like calculator punches. And it's just because this problem is specifically emission and giving us particularly the wavelengths. Yeah.
For the wavelength equation, within the parentheses, is it still n final minus n initial? Would n1 represent n final?
No, right? In this one, and I guess technically yes, right? But the way that the rules are written for this equation is n1 has to be a smaller value than n2, which for emission is always going to be n final minus n initial still.
Okay.
So which n2 would you use?
That's what you're solving for,
Oh, okay.
right? That's the whole point is we know the wavelength, we know the n1, we don't know the n2.
Okay.
That's the whole point.
But isn't N2 like n final? N2 is the same thing as n final?
Not with the way that this equation is written.
Okay.
So because since it's written in terms of n1 and n2, and our rule is that n1 has to be smaller than n2, it's not really saying anything about n final and initial. With the way that this one, and you'll notice, remember I wrote it down as n2 minus n1, 1 over n2 squared minus 1 over n1 squared, because I write it as final minus initial in my head. But on the equation sheet, somebody told me it's n1 minus n2.
Yeah, it is.
That means n1 is the final, and n2 is the initial, which I don't like, but you know. I also don't like this equation that much. It's just particularly for this individual problem. It's going to save us some calculator punches. It's also going to save us some logic, right? Because the absolute value is going to get rid of a negative sign. If you forget that, the most common mistake people make on this is they forget this negative sign, and that can throw your calculation off in terms of what you're calculating. Because essentially, you know, it could be one of two values. So you got to be careful about that. So there's the problem with the Rydberg equations is there's pros and cons to both of them. The reason I like this one that I wrote in green a bit better is because it is more applicable to more situations. This one in black is a little more straightforward, but has some like special rules for when you can use it and how things have to be set up. But as long as you're in those situations, much easier. So, but you know, for me, with the number of equations that we're already going to learn this quarter, I'd rather minimize it and say, let's not learn 2 Rydberg equations. Let's learn the 1 Rydberg equation that's going to be useful to us and work with it from there. I didn't actually do the final calculations. I can't remember what the answers are right now.
Just be solving for N2.
Yeah, N2.
Yeah.
Yeah, solve for N.
It's all for N2. And I'm pretty sure, so one of the fun things we can do just conceptually, let's again go concept-based, right? We know for the visible, N final is 2. What would be the lowest energy wavelength out of our choices? 656. What's the lowest energy transit? What's the smallest energy transition possible from N equals 2 to? So if N equals 2, N equals 3. This could be, depending, and you know, there's always the possibility that they just skip the N equals 3 because it'd be too obvious. But my guess is this would be N equals 3, N equals 4, and N equals 5. That's my guess. I don't know if that's true, but that's kind of we can already set up those like conceptual expectations, right? I know, at the very least, I know that this has to have an initial that is smaller than this N initial. Because the wavelength is much longer, the energy transition is much smaller. Right? I can already get some conceptual information about this. Okay.
Can you maybe do the calculation?
Yeah, let's do the calculation for A. I will do it. Should I do it both ways just so we can see the 2 methods? I'll do it for the equation in black first because I think you know it's just already set up so nicely for that. We're going to have 1 over 121.56 times 10 to the minus 9 is equal to 1.097 times 10 to the 7 times 1 over 1 squared is 1 minus 1 over, I'll call it N2 squared. I'm solving for N2. I'm going to go ahead and bring this 121. I got to do some math in it with a calculator now, but I'm going to bring this, I'm going to invert that, divide by that, and get some equation. I'm going to have 1 over 121.56 times 10 to the minus 9 times 1.097 times 10 to the positive 7 minus 1 is equal to negative 1 over N2 squared. Yeah. So do me a favor, punch that into the calculator. And this is a number 1, that's not an absolute value. Punch that into the calculator and let's get the inverse value. You did not hit submit. So you notice you've got 0 hours still. It's not showing you the totals. So make sure that you, I don't know what button you're supposed to press to make that stuff show up, but right now it's supposed to be 0. So, what do we get for this numerical value? Did no one do it?
Hold on, wait. I thought
They're doing it?
Well, actually, I think I left my calculator in the room on accident.
Oh, no.
I know. Terrible.
Negative 0.25.
Oh, that's great. It's great. So check this out. Negative 0.25 equals negative 1 over n2 squared. I can look at negative 0.25 and I know what that fraction is in my head. 1/4. Negative 1/4. Now, just with logic, without going through all the math, I can say n2 must be 2. I could also say, look, I can cancel out the negative. I can flip both fractions. I can get 4 equals n2 squared. I can take the square root and say n2 equals 2.
I thought it started out at 2.
No, this is A.
Oh, this is A.
This is A. So A is
Starts out at 1.
starts at well,
Right?
ends at
Ends at
1, starts at 2.
Okay.
Right. So, but that's a good check, right? There's a couple things we can logistically, conceptually check for. If you end and start at the same number, you did something wrong. Right? That's not supposed to happen. If that happens, you wouldn't see light, you wouldn't see an emission, you wouldn't see an absorption. If you get a fraction of an n value, if you get like 1.33, that's not supposed to happen either, and it's supposed to be a whole counting number. If you get something that's like 1.99, probably rounding error, probably supposed to be 2. But if you get something that's like 1.33, you probably did something wrong. Right? So there's these logistical checks we can do. What's that?
That's exactly what I got the first time.
Was 1.33? Huh. How'd you get it?
I thought N1 was N initial and N2 was N final, so I
Oh, so you flipped it?
yeah.
Yeah, which is gonna, so the reason that messes
Then
it up,
I think I also forgot to square it.
so the reason that oh, that would also mess it up. But the reason that messes it up is because if you flip those two, that becomes a positive, and that becomes a yeah, because you're gonna add that over. That's gonna totally change your number, right? And that's part of the absolute value problem, right? So if you think about it, you've got some like offset absolute value. You're supposed to be solving for that one. You solve for that one. So yeah.
So is N2 the initial one?
I don't like to make the comparison of those,
Okay.
right? So if you are using this Rydberg equation, N2 is the value that is larger than N1. If you're using the energy-based Rydberg equation, it's N initial, N final, because the ordering doesn't matter. You can get positive or negative energies for the atom. For this one, N2 must be a larger value than N1.
Okay.
And that's part of why we use those different labels for the twos, because we don't want to just try and say, oh, N initial is N2. Like that's works out, but only for emission cases, right? So there's like all those extra caveats that come along with this equation.
Just so we can get a positive value for the wavelength.
Precisely.
Okay.
Because negative wavelength, not our friends. Because they don't exist. Not that you don't have friends. I just mean like they're bad. We don't want to associate with things that don't exist. That was much more awkward than I used to be. So the rest of these, B, C, D, E, all kind of the same logic, same process. I said I would do two. Let's do the 656 nanometers one in the way that I like to do it. So, if we're doing the 656 nanometers, we're doing part D the way I like to do it. We're going to calculate the energy of the photon equals hc. I'll just plug in the numbers for that.
This is the way you suggest we do it.
Because it works in absorption and emission.
Yeah.
So you'd have 6.626 times 10 to the minus 34 joules seconds. You'd have 2.99 times 10 to the 8 meters per second. You would divide by 656.28 times 10 to the minus 9 meters. Meters cancels out, seconds cancels out. This gives us energy of joules. Do you have a question?
No.
Okay. I just want to make sure. We're doing problem 16, part D.
So you have to put it into meters when you're working with the equations. Because
Yes.
it's given to us in nanometers.
Nanometers, correct. And the main reason is because the speed of light is in meters and the Planck's constant is in joules. It's all in SI units, all in meters.
Okay.
So we do this calculation. We get energy of photon. I'm going to say it's like 3 times 10 to the minus 19. How did I do that? 6.5, 6.6, that's about 1. That's about 3. 34, 8, positive 9. Energy of the photon. I should get more digits, otherwise I'm going to get something that's like, I'm going to get something that's like 3.25 if I round too much. But, and so if someone's got a calculator and can tell me actually, but this should be something like 3 times 10 to the minus 19 joules. But I want to know like 3 point what, or is it 2 point something, 2.9 or 3.1 ish?
It's my calculator's just giving me 3 times 10 to the minus 19.
Can I take a look at your calculator for a
Well,
moment?
it's not in, I didn't put it in scientific mode, so it's probably.
Oh yeah,
around
so
there, yeah.
let me put that into scientific mode real quick. Oh,
I did all of them.
3.02 times 10. Oh, and you're off by oh, that's because you put,
I put the saved values.
but you put 10 to the minus 19 on bottom instead of 10 to the minus 9. I was like, why are you off by a factor of 10? That's why. Sorry, by 10 factors of 10.
Yeah.
So that's a lot off. So it's 3.02 times 10 to the minus 19. I was pretty close with just the calculation in my head. So then we can take this and we can say the energy of the photon, 3.02 times 10 to the minus 19, is equal to 2.18 times 10 to the negative 18, 1 over n final squared minus 1 over n initial squared. And you will notice I have gotten rid of a negative sign. How did I do that? So this is one of the logic steps that we need to use. I got rid of the negative sign by using my remember when I wrote this earlier I had an absolute value. I know because this is emission, n final minus n initial is greater than 0, which means if I want this whole thing to be positive so I don't end up with like a weird negative sign, I can essentially say this thing has to be positive for the absolute value to work out. I essentially combine 3 mathematically logical steps that aren't actually doing any calculations together. Conceptually, that's really important, right? This goes back to this idea that the energy of the photon is equal to the absolute value of the change in energy of the atom. Right? And because it's emission, I can get rid of that negative sign and the absolute values. Because I know this is going to be positive, so if I make the whole thing positive, I'm just getting rid of that negative. You do the opposite thing for emission, right? You would leave the negative sign there, or flip the order. Like you leave the negative sign there if it's emission, you get rid of the negative sign if it's, you get rid of the negative sign if it's emission, you leave the negative sign there if it's absorption. And that takes care of the absolute value, that logical step. Then we can go ahead and we can plug in the fact that we know n final is equal to 2. 2 squared is 4. And now we're just doing the same mathematical solution stuff we did before. I'm going to have 3.02 times 10 to the minus 3.02 times 10 to the minus 19 divided by 2.18 times 10 to the minus 18 minus 1/4 is equal to 1 over n initial squared negative. Don't forget that negative. That negative sign you can't get rid of. We already took care of the absolute value. You can't just get rid of any negative sign you feel like. Got to be controlled about it. And that should, hopefully that works out. That's like 3/21, that's like 1/7 minus 1/4. That's going to be a negative thing. That should work out. I hope. But notice, after we do the logistical steps of recognizing what part of the spectrum is and what n final is, we're pretty much just using an equation. You can just leave it on the desk. We're pretty much just using an equation. We have to be careful about the conditions in which that equation applies. As long as we're careful about that, we're just doing algebra. Right? There's a lot of thinking that we need to do to get to that algebra, but then we're just doing algebra. Did anyone get an answer to that? No. I'll actually pick up the calculator. Let's see. 3.02 divided by 21.8 minus 0.25. I think something that's like 2.99. Now, if you report 2.99 as your answer, I'd probably take off like a part of a point. Because we know that the n values need to be whole numbers. And what we're dealing with is just rounding errors. It should be 3. Which, if you remember, was what we guessed would be the case for D. Because it's the smallest energy transition possible. Our guess wasn't that bad. So that's how we do problem 16.
Wait, why does it go 2 and then 5, 4, 3, 6? So it jumps up a lot of numbers. So it goes like low, and then when it like switches from UV, or no, UV to visible, it goes like up a lot. Like, not mathematically, but like I understand why it happens mathematically, but why would that be?
So if we're thinking about UV, our n final value is always going to be equal to 1. For hydrogen, right? This is just for hydrogen. And our uninitial value has a whole slew of possibilities. If we're looking at the visible spectrum, our n final is equal to 2, and our n initial is a whole slew of possibilities that's bigger than 2. And that's our restriction for hydrogen based on the quantum mechanics and based on the physical observations. And those two things match up really nicely, which is like, thank goodness theory works. So I'm not sure I totally understand your question, but did that clear it up?
So I was just wondering like why like the numbers like jump up, but like the n initial which we're solving for, it like goes from I think it was 2, and then it goes, and then the next one B would be like 5 or 6.
That was because the n final also changed, right? So I see what you're asking about now. That's because what we're looking at for these wavelengths is energy difference. And when you change your n final, that's a dramatic change in your energy difference, right? Because this is like, so you'll notice in the problem we did for part A, this was like 1 minus something. For this part, it's 1/4 minus something. So that's 0.75 different. And that's where that difference is coming from. We're good in problem 16. I feel like y'all could do 17 and 18. I feel like it's an extension of these ideas.
7, 18.
Yeah, could you set up
17's a little
Then
much.
I'm confused.
17, I'll just tell you 17 real quick because it's a very algorithmic problem. Very just doing algebra. as long as you recognize the equations you're supposed to use. You're supposed to use E equals hc over lambda, nu equals c over lambda. So if you have wavelength, and then you could also do E equals h nu, which is, these are the three equations. You put these two equations to make that equation. If you have the energy, this gets you the frequency. If you have the energy, this gets you the wavelength. If you've got the frequency, this gives you the wavelength. And you're just solving for those three, so you're just using these equations as necessary. That's it. That's all you're doing for problem 17. All the stuff about lasers and like the cool lasers that you can do this with, it's just interesting context for doing these calculations. Yeah.
It also asks for the color on 17. We'd just be looking at the wavelength in nanometers.
Yep.
For that, but should we have like a specific like range memorized for each of the Roy G bibs?
I would give you that color wheel with the. I would give you the Roy G bibs.
Okay.
I would give you the Roy G bibs. I wouldn't ask you to memorize that. I don't have it memorized.
Okay.
Maybe I've got it kind of memorized, but that's just experiential, not actually trying to memorize it.
Okay. Cool.
So that's 16. That's pretty much 17. Number 18. Oh yes. So number 18 is kind of this funny, like, hey, sound waves and waves are waves, whether they're sound or light. So if you think about light, use the nu equals c over lambda, or nu lambda equals c. This is frequency. The other way to think about this is frequency times wavelength equals speed. Same concept holds for sound waves. It's just your speed is no longer the speed of light, it's the speed of sound. So if you've got the frequency and the speed of sound in air, you can calculate the various wavelengths. That's all you got to do.
Okay, so c isn't like just constrained to like the speed of light. It can be any speed.
Whoa! No, this is two different things. So c is specifically the speed of light. This equation, just light. This equation, really any wave.
Okay. Got it.
Right? And it just happens that light is a wave with a particular speed.
Gotcha.
Yeah, but that was one of the funny things. I do have students who are like, oh, so the speed of light can have multiple values. I'm like, no. A wave can have multiple speeds, but light is a wave with a particular speed.
Doesn't matter what it's going through? Or does it?
Debatable? Not entirely debatable. Like, definitely, we're talking about the speed of light through, actually the equation we're using, the 2.99 is light through a vacuum, right? We can modify that for light through air, but it's like 2.991 blah blah blah. It's like down in the 6th digit or something like that. There are certain materials, so like for all intents and purposes, it's just the speed of light. But there are some people who, there are some researchers who say they found materials with weird light properties, where they can get the light jumps across the material faster than it's supposed to, which shouldn't be able to happen. Speed of light is like supposed to be the upper maximum, and this was a paper that I saw like 8 years ago, and there were already a lot of people who were like, this is dubious. And I haven't heard about it since, so my guess is they were like, oh, actually we were off by like, a digit, and it turns out we didn't do anything that cool. Because it's like the data they reported was 8 sig figs, and the variation was in that 8th sig fig, and it was like if your measurement averaging was like done in a favorable way, you would have seen this effect, and if it was done another way, you wouldn't. And so there were a lot of people who were like, it was also considered like a great example of like statistical manipulation. And you know, they didn't do it intentionally, but that's where you got to be like really careful with how you're doing data analysis. Oh, it's gonna be a long day. My throat's already tired. So that was all the homework questions. Were there any? We talked about some lab questions. No, we didn't do lab questions yet.
I have a lab question.
Mm-hmm.
So, when we're solving for NI, or we're supposed to solve the Reiber constant, do we get the NI value? Do we use the Reiber constant? Like, how do we get the NI to solve?
Ooh, great question. Do you know what NF is?
Yes, too. For
What could NI be?
anything higher than that.
3, 4, 5, 6, 7, 8, 9, 10. What's your, so we're going to do the same logic that you, I'm not sure when you showed up for it. So if you looked at it, what's your lowest energy transition? Let's go ahead and do like a quick hydrogen kind of map for energy levels. This is n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and we can keep going, right? I just don't feel like writing that many. I gotta hide the marker I just picked up now. What's going to be our smallest energy transition possible?
3 to 2, right?
3 to 2 if we want to keep visible. What's the smallest wavelength of light that we observed from hydrogen?
I don't recall.
Violet?
Oh, sorry, smallest energy of light,
Oh,
which would be the largest wavelength.
that'd be the red.
Your red line is going to be n equals 3 to n equals 2.
Okay.
What was the next highest energy line we saw?
4. Blue, green.
I'm going to go with blue.
And we know that like it's emitting,
And I'm going to go with, yes, it's emission for sure.
and we know that it's like between each of those.
And we,
And 2.
well, so we know it has to end with n equals 2 because it's visible.
And it
I'm
can't,
going to
like,
go with this black line because I don't have a purple marker, but that would be our violet line.
So is it the same for all of the different gases where it goes the first line is
No.
okay.
So for mercury, for argon, for neon, it's not this simple.
Okay.
Which is why we're doing it for hydrogen, and we're just going to be like, oh, we know the wavelengths for mercury already, right? But really, this would be much more complicated if we wanted to do this calculation for mercury. Yeah.
And like for hydrogen, there's never really a time where we just like skip 3, like with the emission from like.
What do you mean?
So like hydrogen doesn't like skip any levels. So if you go from like 3 to 2, then no, 3 to 2, 4 to 3, 5, no. But it just always goes like 3, 4, 5. We're not ever gonna go 3, 5 and skip that.
Like this? Like these transitions?
Mm-mm. I'm not very good at phrasing questions.
Okay. So the n value always counts every whole number. So we're not going to ever skip n values. Right? So you're talking about transitions?
Mm-hmm. And I'm just like saying is there ever a time where like 3 isn't counted? Or like.
Well, so if we looked at this, if you looked at this one, 4 to 2, you're just kind of skipping the 3, right?
Mm-hmm.
So we don't really need to deal with the number 3 in that case.
Alright.
What we care about is the magnitude of this energy transition.
Mm-hmm.
Now, you can get into some interesting debates about whether it's a single photonic or a multiphotonic process, but like, you know, we're just jumping. So this n equals 5 to n equals 2 transition would skip over 4 and 3, and you just have to do the difference between 5 and 2. Is that more what you were thinking about?
Sort of.
Okay. But also, all of these transitions I'm drawing in yellow, or sorry, orange, color's difficult. All of these were also happening in your observation. It's just our eyes cannot detect them. The cameras on your phone cannot detect them. But they were all happening because we weren't doing anything to actually control the energy that we were inputting into the system. So all of that was going on as well, but The only ones that we can optically detect are those. If we get some cool scopes and if we get some detectors that can detect in the ultraviolet, we could actually look at these different series. If we got some detectors that actually worked in the infrared, we could detect these other series.
So, I'm sorry, I'm forgetting. Which gas was this? Was this hydrogen or mercury?
Hydrogen.
Okay.
Hydrogen. Mercury, yeah, hydrogen is the only one that really works this simply.
Okay.
Because it's one proton, one electron.
Oh, just, yeah. Okay.
Everything else gets a lot more complicated real fast.
Okay.
I had a question more specific to my own data about the.
Well, let me check real quick. Does anyone else have broad questions
I have
about?
a very general question.
General question, because I'm going to stop the video.
Alright,
Yeah.
so it was, do we need a standard calibration curve for all of the things, or just the one?
Just the one.
Just the one, okay.
Just Mercury.
Awesome.
And then we're using Mercury to figure out the wavelengths for everything else. Any other broad questions that might be good for
in
video?
in LabPal, if we put in a wrong answer, are we losing points?
I have to double check the way I have it set up. I don't think so.
Okay.
As long as you get the right answer eventually.
Yeah.
This is the same thing with like the reading quizzes. Like the whole idea with LabPal is you get feedback, but you don't really get penalized. So that's but I have to double check. I think there's a setting where I could have it take off points, but I think I turned that off because I wasn't interested in doing that. Any other questions?
Just specific stuff.
Cool. Okay, I'm gonna go ahead and stop this video. Hope you all enjoy it.